Comprehension chains.
Well, thank you. Actually, I won't be talking about affectuses. So affectuses are a categorical framework that we in Nijmegen are studying to capture the semantics of computation and the semantics of quantum computation in particular. And in our studies, we recently discovered a very natural phenomenon I wish to speak to you about, namely a chain of adjunctions. So I don't know whether this, you can see that the picture is built up from the authors of the paper, and you can see the adjunction signs here. So the intended meaning of this picture is such a chain of 5 functors and 4 adjunctions. So you can compare it. so for such a chain of adjunctions, the left one I would like to call quotient, and the right one comprehension. And this whole thing is a quotient-comprehension chain. So let me start with an example. So vector is the category of vector spaces of linear maps, and then L sub is the category of linear subspaces. So there's an obvious forgetful functor down here. So to a linear subspace, you assign the vector space to which it belongs. So by I denote a linear subspace by this pair. So S is the subspace and V is the vector space to which it belongs. So S is a subset of V. Well, so those are the object of L sub, but there should also be morphisms. The morphisms are exactly what you expect. So a morphism from a linear subspace S to a linear subspace T is just a linear map from the surrounding vector spaces V to W, which maps the one subspace into the other. Now, if you replace T here by W, then this requirement becomes trivial. So then we get this bijective correspondence. This means that we have a right adjoint here. Similarly, you can do this and you get a left adjoint. So you see that the forgetful functor from L sub to vect has a left and right adjoint, and I will call this one 0 and this one 1. So just an abbreviation. And so now the interesting thing is that there's also a right adjoint and a left adjoint. So the right adjoint to 1 takes a linear subspace to itself as vector space, and the left adjoint to 0 takes a linear subspace to the vector space modulo this subspace. You might think, well, this is interesting, but what does it have to do with quantum mechanics? Well, I'll address this, so I'll replace vect. Oh, wait, I'll call this one comprehension as quotient. I'll replace vect with help. So now it has to do with quantum mechanics. But then I should replace linear subspaces with closed linear subspaces. Because otherwise the comprehension is not a Hilbert space anymore. But then the same goes through, except one might wonder, what is this quotient? If you do a follow course on functional analysis, you probably won't have seen a quotient of Hilbert spaces. Or at least not in this form. That is because it is simply the ortho complement. And now we see something very interesting. So the quotient and the comprehension starts to look somewhat alike. So what we can do now is we can take the co-unit of the quotient adjunction and the unit of the comprehension adjunction. I will call those things quotient and comprehension as well, and compose them. So then we get a map from the vector space V to itself, which I will call assert, for reasons that will become clear later. And this map, since this is just the inclusion, and this one is the projection onto S, this will be the projection into S. So given a closed linear subspace, you can get the projection onto S by this composition. Alright, so this is curiosity, but not very deep. But I will show you that for another chain of adjunctions, we can get this thing. And this thing, called the sequential product, has been extensively studied by Goddard and others. And with this thing you can define quantum measurement. Well, to be fair, not every measurement. For instance, they cannot capture continuous measurements. And also not one where you have unitaries here. But you can get unsharp measurements with this thing. And it is, so Chris talked about effectuses. And the aim of this work is to include measurement into an effectus using this chain of this quotient-comprehension chain. So we've already seen. So in this talk, I will give you many examples of quotient-comprehension chains, and I've already shown you vector spaces and Hilbert spaces. I will also show you Boolean examples, probabilistic examples, and finally a quantum example where you will get this square root a b square root a. So let's start with the Boolean example, namely the categories of sets. So again, we take a category of predicates, namely in this case they are subsets. And there's an error here. So to a subset S of a set X, we assign X. So this S should be X. Let me try to change it. And then it will disappear now. So again, if you assign to a subset the set it is contained in, then you get a functor here, and you have a right and a left adjoint. A map from a subset to another subset is what you expect. It's a map between larger sets, which maps the one subset into the other. You have a 0 and you have a 1. And now you get a right adjoint. It is simply mapping the subset to itself, and you get a left. Wait. Well, it does not quite work like this, unfortunately. The 0 does not preserve the final object, so there cannot be a left adjoint here. Fortunately, there's a solution to this problem, because I do want to show you a lot of quotient-comprehension chains, and that is to replace sets with maps with sets with partial maps. So the category of sets with partial maps is the same as the classic category of the Westerbaan net. So I'll denote it like this. And then you do get left adjoint. So then we have a quotient-comprehension, and the quotient is mapping a subset to its complement. Note that this is very much similar to the Hilbert space case, where we mapped a closed linear subspace to its ortho complement. So again, we can compose quotient with comprehension, and this time we get an assert map which maps elements of X to itself for elements from S, and is undefined otherwise. So this is again similar to the Hilbert space case, where in the Hilbert space case we have a projection, and here we have a projection, but then the partial map varied to that. So this is for the category of sets. There are many variations possible, and I will go through them quickly. You can also take topological spaces with Knopen subsets, or measurable spaces with measurable subsets, or compact Hausdorff spaces with Knopen subsets. This is not a special case of the topological case, because here we need the fact that a closed subset of a compact Hausdorff space is again compact. But still, I wanted to show you this example because it's interesting for another reason. The category of compact Hausdorff spaces is duly equivalent to many algebraic categories. For instance, the category of C-star algebras with MIU maps. So then from this example you immediately get also a quotient-comprehension chain for commutative C-star algebras with star homomorphisms which are subunitary. So then in that corresponds, the closed subsets correspond to indicator functions of the closed subset. So then the predicates in the case of commutative C-star algebras are projections. There's also another algebraic-ish example of a quotient comprehension chain, namely commutative rings, which does not have a spatial counterpart as far as I know. Oh, and there's another error here. This should be E and this should be R. In this case, the predicates are idempotents. All the previous examples are a special case of this. They are all extensive categories. If you do not know what an extensive category is, you can safely ignore this. Every extensive category is, no, every topos is an extensive category, so there's that. And so then we have these Boolean examples. Well, let's now go to the probabilistic examples. So let's start with the classic category of the distribution monads. So normally a map assigns to one element another element. But a morphism in class 3D assigns to an element a distribution, a finite distribution of elements. So notice that there's here a +1 again. That is because we need partial variant of this. And that corresponds to the classic category of the subdistribution monad. So morphisms in the classic category of the subdistribution monad assigns to an element a subdistribution of elements. Well, then again, I'll just show that elements of the subdistribution monad are formal subconvex combinations. And then, in this case, the predicates are maps from X to 0, 1. So these are called fuzzy predicates. The morphisms in the category pred are a bit more involved. They are morphisms in the underlying category, but now with this requirement, or at least this is what you would expect. But this is not quite right, because defined like this, we don't have a right echoed. I'll skip the reason because I don't have time. But the way to correct this is to add this factor here. So then we do get a chain of adjunctions, and let me just point out the comprehension here. The comprehension of a fuzzy predicate P are all the points where P is exactly 1. The quotient of P are all the points where the 1 minus P is greater than 0. So these are all the points where P of x is not 1. So I want to show you this assert map again for this case. But to do this, I need to change this a bit because we cannot compose these two sets yet. So this is a number between 0 and 1. So we can take the integer part of this. So so this thing is greater than 0 if the smallest integer above it is 1. So then if we replace this thing, if we make a shorthand for this like this, then we can abbreviate this like this, where the ceiling and the orthocomplement are taken pointwise. And now we see that we can compose quotient and comprehension. Namely, we can first do the quotient of P per, and then the comprehension of the ceiling of P. I have not explained what the unit and the counit are, but I hope you'll believe me if I say that the assert map that you get for P assigns to an object x, but then weight with the predicate P. So there are many variations of the subdistribution monad as well. For instance, we can do it for the Giri monad, and I also think for the Raman monad, but I won't go into that. So now let's get to the quantum case. I think this is really the exciting case. So to get a quotient comprehension chain for operator algebras, I would start with this. So this is the category of C-star algebras, not necessarily commutative, with positive subunital maps. There's an op here because in the case of quantum computation, everything gets turned around. And here, a predicate is an operator between 0 and 1. These are usually called effects. And the morphism here is from an effect P to an effect Q is a map in the other direction, like this. So here you see this correction term again. And now we do get left adjoint to the forgetful functor and right adjoint to the forgetful functor. But actually I don't know whether there is a left adjoint here and right adjoint here. Maybe if somebody is very well versed in functional analysis, he or she can tell me whether there is. Because I could only answer the question whether there is a left adjoint for the case of W star algebras, for normal algebras. In that case, the left adjoint is the quotient of a predicate of an effect P is this normal algebra. It is so this thing here is a generalization of ceiling, a generalization of integer part. So the ceiling of Q is the least projection above Q. So this thing does not necessarily exist in the C-star algebra. Here I use the fact that we are dealing with phenomenal algebras. This space consists of all the operators, which are of the form ceiling P perp A ceiling P perp. But even now that we switch to phenomenal algebras, I still don't know whether this one is a right adjoint. So, to solve this, we actually needed to turn to completely positive normal maps. And then we got a compression here. Here the floor of P is the greatest predicate below P. And then because we changed the category, this thing is again unclear, but it turns out to be alright. And that uses the fact that complete positivity and normality are closed in the ultra-weak limits, if that says anything to you. So, I want to emphasize that I cannot show it to you, but the proof is non-trivial. Well, functional analysis is non-trivial, but it also uses things that are not well known within functional analysis. For instance, this generalization of the Cauchy-Schwarz inequality for two positive maps. I could only find it as an exercise in a book of Vern Paulson. So I carefully checked whether it is indeed true. Now let's get to the assert map. We can, if we compose the quotient and the comprehension, they go in the other way now. Then we get, and you have to believe me on this, then A gets mapped to that thing which gets mapped to the square root B, P, A, square root P. So this is what I promised you. So then one might is tempted to say, we have a universal property for square root P, A, square root P. But this is not quite right, because we have a universal property for comprehension, and we have a universal property for quotient. But this thing is the composition of those two. And in fact, we can plug in between quotient and comprehension, we can plug in unitary, like this isomorphism. And then the composition of quotient with this isomorphism is just as well a quotient of P perp as only this map. So then this thing is has just as much rights to be called the assert map of P as well. So this is an issue we are trying to deal with. And it boils down to getting some coherence between this quotient and this comprehension, but we've not figured out how to do that yet. Of course, you can replace for normal algebras with normal completely positive subunit maps with finite dimensional C-star algebras. Then everything becomes easier. And then so we have also quantum. So then we have these quantum examples. And there's one last example that I want to mention to you if you would like to think about these things. Namely, if you want horrendous counter examples, I would suggest you look at order unit spaces. Well, thank you.
You have time for some questions?
Can I ask a question?
Oh, sorry.
So what inspired you to find this structure? It's quite an interesting, subtle structure, this chain of the junctions and so on. How did you excavate that? You see, did you dig it out?
How I came up with it. Also, that's actually an interesting story. So, what we were trying to do, Bas and I, we were trying to find a universal property for this thing, and the only universal property we found was that of a quotient. So this map, from this type to this type, this will actually be map A to the square root of PA squared B. However, A is not equal, so this is not the same space as this one. So then we needed to have a universal property here as well. So we concretely found these universal properties for these things for the von Ormy case. And then Bart took a look at it and he said, well, but this is just a chain of junctions. And that is how we came up with it. Then all the other examples came before. After, so this is, I showed you the wrong, I showed you the didactic order, not the chronological order.
So, to me, this looks just like the issue of looking at what a POVM does to a state, right? That's not necessarily unique, it's just a kind of choice of convention that you take a positive square root to be a kind of solution. So is it the sort of same phenomenon?
Perhaps, there's an internal discussion in our group whether whether this thing is special or not. So some of us would like to say that we cannot expect there to be a universal property for this thing because this one is just as good. But that doesn't work well. If you then have a category and then if you don't get a unique map, that's not nice. You would like to have a unique instrument map that makes it easier to program with it.
Okay, thank you.